Good morning, gentlemen. Today is Tuesday, June the 2nd, and today we are going to continue our discussion of modern physics by talking a little bit about the structure of the atom. Now, everything that I'm going to talk about today is stuff that you should have learned from Mr. Leonard last year. And I'm going to assume that you did, because Mr. Leonard is very smart and really knows his stuff. But I just want to review it a little bit so that we can get into tomorrow's lessons on how this affects physics. Okay, so in any event, that's kind of where we are now. Now, you may recall from chemistry class that the first real model of the atom was put forth by a guy by the name of Dalton. All right, now Joe Dalton built a model, or imagined a model of an atom that was almost like a chocolate chip cookie, where most of the atom was, positively charged dough, and there were some negatively charged electrons embedded in it, kind of like the chocolate chips in a chocolate chip cookie. But in more recent time, and Dalton was probably 300 years ago, maybe, I'm not absolutely certain. But in more recent time, in the early 1900s, a guy by the name of Joseph Thomson said that electrons are relatively low mass and negatively charged particles. Now, Thomson was able to actually calculate the mass of an electron. It was actually Robert Millikan, who we already talked about, who discovered the charge on an electron, but both agreed that they were relatively low mass, negatively charged particles. But Thomson also realized that since atoms were electrically neutral, then part of the atom had to have a positive charge that was equal to the total charge of the atom's electrons. So if you knew how many electrons the atom had, then you could conversely figure out what the positive charge was on that very same atom. And so Thomson kind of extended Dalton's model just a wee bit and proposed a model for the atom in which, again, there was a uniform distribution of positive charge in which the electrons were embedded. Excuse me. Today, we kind of think about this as, again, the chocolate chip cookie model, where the chocolate chips are the relatively negatively charged particles, the electrons, embedded in a big gooey mass of positively charged dough. Okay. Now, moving along from Thomson, right, it wasn't so much longer after Thomson's time that a guy by the name of Joe Rutherford came along, and he is responsible for what is now famous as the gold foil experiment. Now, essentially what Rutherford was able to do was to take a radioactive element and put it inside of a lead box with a long tube that came out of it. And essentially what he created was an alpha particle gun. Now, an alpha particle is a radioactive particle. It's essentially a helium nucleus. So it's composed of 2 protons and 2 neutrons. So it's heavy, relatively speaking, and positively charged. And he shot these alpha particles at a piece of gold foil. And he found that most of them just passed right through it, as if it wasn't even there. But some of them were deflected. And he started to question why they were deflected. And his conclusion was that atoms consist of small, dense, positively charged particles, the nucleus, surrounded mostly by empty space. And he reasoned that inside that empty space is where you would find the negatively charged electrons in orbit around the nucleus, kind of like the planets are in orbit around the sun. All right? Kind of. All right? So that was Rutherford. And so now we're getting a more and more clear picture of what an atom actually looks like. So now we've got this big, fat, massive, positively charged nucleus surrounded mostly by empty space in which the electrons are moving around it. So the question is, because opposites attract and the nucleus is positively charged and the electrons are negatively charged, how come they don't crash right into the nucleus, right? They should be attracted after all. Well, the answer is kinetic energy. The electrons are actually moving so fast that they literally orbit the nucleus. Again, just like the planets orbit the sun. Their tangential velocity is so great that even though they're falling toward the nucleus because of this electrostatic attraction, they never actually get any closer to the nucleus because of their great speed, their very high kinetic energies. Now, it wasn't until the early 1900s, I think it was in the 1930s and 40s, that Niels Bohr came up with the orbital idea, or the shell idea of the electron's orbits. And what Bohr did was he looked at this in terms of energy. Rather than particles in motion about each other, Bohr looked at the electrons as energy carriers almost. And he said that all forms of energy are quantized, all right, meaning that they have a specific amount of energy. And electrons can only gain or lose kinetic energy in very fixed amounts, which he called quanta. Excuse me. Now, you've probably seen this picture or one like it in the past. Think about this. When you climb a staircase, you can either be on the first stair or the second stair, but you can't take half a step at a time, right? Because you fall right back down to the first step. Okay? So either you go up to the second step or you stay on the first step. And Bohr looked at the energy that electrons carry in a very similar fashion. He essentially said that either an electron can be in a first shell, or it can be in a second shell, or maybe even a third, but it can't be in between. And the way that it gets from one shell to the next is by either absorbing a certain amount of energy and moving out away from the nucleus, or by releasing that same amount of energy and dropping back down into a lower shell. And you can see the model here, right? Whoops. Come on, there we go. All right, so if you've got an electron orbiting, and I'll call this the lowest energy level, or the first shell, if I absorb a certain amount of energy, I can jump up to the second shell, and you can see that here. And if I'm in the second shell and I absorb this amount of energy, I can jump up to the third shell. And if I'm in the first shell and I absorb both of those amounts of energy equal, then I can jump up to the third shell all at once. And the same thing goes for the way back down. So the electron itself can jump from one orbit to a higher orbit by absorbing a quantum of energy. And the reason that this relates to what we've been talking about in terms of modern physics is because the energy that's absorbed is absorbed in the form of a photon, all right, a quantum of energy that we call a photon. Okay. Now, so Bohr then constructed his model of the atom, given all of the various pieces and parts that we've just talked about. He said that the electrons were moving in very specific orbits that corresponded to a specific amount of energy. All right? And again, that energy was absorbed all at once in terms of a photon, a quantum of energy. And so each allowed orbit in the atom corresponds to a very specific amount of energy. And we'll talk about the numbers that are associated with this during tomorrow's lesson. Now, the orbit closest to the nucleus represents the smallest amount of energy that an electron can have. In chemistry, you used to refer to this as the lowest energy level, or the resting energy level. And so when you talk about the first electron or the second electron, they're always going to be in the lowest shell, unless that atom absorbs a quantum of energy, in which case they jump up to the next energy level, and then the next, and the next, and the next. And of course, if you add enough energy to the atom, eventually you form an ion, because the electron is removed from the orbit of the nucleus. Now, the electron remains in whatever orbit it happens to be in without losing any energy, even though it's got a centripetal acceleration, right? It's moving in a relatively circular path around a nucleus. And a centripetal acceleration means that there's a centripetal force, which is pulling it toward the center, the nucleus in this case. However, because it has so much kinetic energy, and there's this tangential velocity associated with the movement of an electron, it continues to orbit around and around and around without ever crashing into the nucleus itself. Now, the centripetal force there is caused by the electrostatic force, or in this slide I refer to it as the Coulomb force. All right, and you can look that up back in your electricity formulas. F equals K times Q1 times Q2 all over R squared. But we'll revisit that at a different time. So everything that I've told you today is just a very brief review of the structure of the atom, which is probably the second or third unit that Mr. Leonard talked about with you last year. So it's almost 2 years ago that you learned about this stuff, but I'm hoping that it's still fresh in your heads. Now, Bohr also said, he had a few other things to add to this in terms of his idea of energy levels. Right, in terms of where the electron actually sits, that depends completely upon how much energy the electron has. The more kinetic energy it had, the further and further away it would be. Now, how did it get that kinetic energy? Well, it gets it by absorbing these quanta of energy. Now, in terms of the energy levels themselves, depending upon what atom you're talking about, each orbit will be different. All right, so a hydrogen atom will have different orbitals, different energy levels than a helium atom, which are different than a lithium atom, which are different than a mercury atom, which are different than a uranium atom. All right, so just because you're talking about the first shell doesn't mean that the electrons in the first shell of a hydrogen have the same amount of energy as the electrons in the first shell of a sodium or an aluminum. Okay, so the electrons themselves, according to Bohr, can exist only within certain orbits, and this is based on the amount of energy they have. If you add or lose energy based on the absorption or emission of a photon, the electron then takes what we call a quantum leap. You may have heard that term before, but this is what it means. But the electron then takes a quantum leap up to or down to another energy level. All right, so if you absorb a photon of X amount of energy, you jump up to the next energy level. If you then emit a photon of the same amount of energy, you jump back down to the previous energy level. Now, this leads us to the question is, how much energy does it actually take to remove an electron from an atom completely? All right, especially if you're talking about an electron that starts out in the very first shell. Well, that amount of energy, which is usually composed of multiple quanta, is called the ionization potential. And this is simply defined as the energy required to remove an electron from an atom. How much energy does it?
It's 9 o'clock.
Oh, thank you, Jesus. But how much energy does it take to remove an electron from an atom? All right, and that's the ionization potential. All right, my friends, that is all that I have to tell you today. For tomorrow, we'll talk about specifically the numbers that are associated with these quanta. All right. So happy Tuesday, and I will see you tomorrow.